Good. So just to inform everyone, also you, tomorrow we will not have the lesson because I have some important things to do, but on Friday it's as it's planned. So Friday, we meet again on Friday at 11. Does anyone have any questions from previous days? Okay, if not, let's continue. Just a second. So, okay, first of all, at the end of today's lesson, I will send you also this notebook so you can go through it and check everything again, do some stuff. And here I put at the beginning of the Jupyter notebook, I've written some link. You can go to this link and just go through the manual. This is so-called new manual of seismological observatory practice. It's not really new, it's from the year 2012, but you know, many things did not really change. So this is basically a very long book that you can find here on the GFZ website. If you go through these pages, you will see many different subjects that you may be interested in. So let's say here you have a chapter on seismic source location, or maybe location at teleseismic distances from one station, how to do this. And this also comes, as you see, with the tutorial, not just it's not just written stuff. Seismic waveform data retrieval, this is I'm sure it's very old because today this is done slightly different, but just go through this titles, find something that you're interested in and read it. I'm sure everyone can find a lot what you are interested in. Okay, so I mean, this is something for you. It's quite interesting. The chapters are not so long, so and it will give you a lot of information. So what we will do today is we will write some codes and use them to pick the phases of earthquakes. So we will try to detect some earthquake inside of our waveform. We will try to pick the phases. We will see how automatic detectors work. Then we will compare these picked phases with calculated phases. So if you take a velocity model, you can calculate theoretical arrival times. What else? Then we will try to calculate the magnitude of this event, and we will try to locate this event. For the location, I can show you where you can get the software that we will use, but I mean, you can try to set it up on your computer and use it, but it's not so straightforward. It's a bit complicated. There are many things that you need to do with this software, but it's very powerful. So it's, if you will work with earthquake locations, this is useful to check, but more on this later. Okay. So as always, we need to first do some imports. And so here, there are two more functions that I defined here. So the first one is like always for plotting. And then I have two more. One is called max pose finder. This is basically what this function does. It's when you give a waveform, it will try to find the location within the waveform of the maximum amplitude. So of absolute maximum amplitude, and the function will return the position of this maximum amplitude that is read in the data set. This is just, as you will see later, this will be just used for plotting. It's not really needed. And then the second one is local magnitude. So what we do inside of this function, we give this maximum value of some seismogram. We set epicentral distance. Here it's hard-coded to 29 kilometers, but you can change this. Let's say if you know how far your earthquake is, you can always change this to some value. But because this would later complicate it a bit our code, we can do it if we can we can make this more real. Then here, so we take this maximum value and do this calculation on it. Why? Because the local magnitude formula that we will use to calculate the focal, the magnitude is actually logarithm of the value, so the maximum amplitude, times this number, because we have to convert the value to micrometers. And if you remember, our data set is in meters. The displacement, when we remove the response, it goes to meters, so we need to get to a lower number. And then plus 2.5, this is some correction, times logarithm 10 of epicentral distance minus another correction. This is a formula for computing local magnitude in I don't know which country exactly. I think I took it from Switzerland. So each country will have probably slightly different code because, I mean, different formula, because this is empirical formula, so it's tested on many events and depends on your crustal velocities and stuff like this. This needs to be appropriately set. So let's say in Ghana, I'm sure they use different one. I know that in Italy, for local magnitude, you have many different ones, not just one. It depends on the region where you are, and so on. But this local magnitude is only calculated. It's not so informative. It's only calculated for small earthquakes, but for larger earthquakes, you should always calculate the moment magnitude, because it's much more. It tells you much more, but it's more complicated to do it. So I didn't try to implement it. I don't know if I know how to. So, okay. First, let's talk about the earthquake detection. So as you know, we have to, when we have a big waveform data set, let's say we install 100 seismic stations in, I don't know, in Vietnam, around the fault. What is the big fault that goes through Hanoi? There is a huge fault. Yes, I know. I was there, I saw it. So there is a big fault that we want to study. We set up 20 or 100 instruments, and we have few years of data. And now, of course, we need to process this data to see what's happening. So we need to build our earthquake catalog. This is, of course, I mean, the basis for every study. So you have to do it. So first, in short, in old times, if you know, in the old times, this seismic data was always recorded on paper drums. So everyone was looking at that and tried to see if they see the earthquakes. This was a completely analog era. Then they developed digital seismographs. So the old ones, you put them on the ground and it was recording. And when strong shaking happened, the seismogram triggered, and it stored the data. So this was, you did not get a continuous data set like you get now, but just cuts of the earthquakes. So all the recorded noise was thrown away. But today we have these continuous data sets because we have enough storage, we have good internet connections, so we can even send this in real time to the center. And on these continuous data sets, we can use many different detectors. So the one that we spoke about yesterday, and we will try to implement it on Friday, I think, is the easiest one, the STA-LTA. Then you have many other different detectors. One is also this similarity detector that we talked about yesterday, and I will show you how it works also today or on Friday, depends on how much time you have. And then the third, the new modern ones is the machine learning algorithms, which work very nice. And I think that in the future few years, this will be used in every seismological center in the world. So the question is, of course, what makes the earthquake different from the noise? Of course, this is the amplitude change. When if you look at the noise, you just have some random wiggles going up and down, not much. But then when the transient signal comes, like earthquake, the amplitude will change quite a lot. Now, this is not always true for very small earthquakes. As you saw yesterday in some examples that were of the small earthquakes that were not detected, this change in the amplitude is not so big. Then you can also look this in the frequency domain. So you are observing frequency changes and you run your triggering on this. This is very nice, it works. But then here you can see the problem is with the low frequency earthquakes. Somehow, I mean, in general, these low frequency earthquakes, I don't know if you talked about them, maybe you will with Karim on his lectures, but this is a specific kind of earthquakes that normally happen on the subduction zones, but very deep on the crustal faults. More or less, they're quite rare, at least, I mean, not in the subduction zones, but in other, let's say, tectonic settings. They are quite rare. If you find them, you are a lucky man. I was also looking for them, but failed. And then the third thing that makes earthquake different from the noise is also this polarization changes. So this means that if you look at the noise should look completely random, but with P and S wave phases, you can see the polarization. So it goes up or down, or when you look at the different components, you can also see these things. So, okay, now let's do this. First, okay, here let's first we need to we will look at some data. I will show you one of the STA-LTA methods. As you can see here, here are some links. You can, maybe I will put this to your exercise to do. So you can use different, with OBSPI, you can use different kind of detectors, which are already implemented. So if you go to this link, there is a trigger picker tutorial for the OBSPI, and you see that here you have some different triggering methods available that you can try to play on your own. You will see how different one works and which is better for what. So this is one thing, and in this example here, we will use this recursive STA-LTA filter detector. I will say some words about this. Okay, so last time I downloaded the data to this directory, and now let me read this data and make plot. Of course, I did not start here, sorry. Okay. So this is our earthquake detected by many stations and many channels that happened in Slovenia, magnitude, I think, 1.4, as given by the local seismological survey. So now we will, for the ease of use, so that it's not too complicated, I will only select the vertical channel of every station. You see here, I do this with our stream. So this ST event, select component Z. This is vertical, and I will select only one of the stations, so the third one. Then I will filter this with a high-pass filter with a frequency of 2. So let me first make a lot of this. So this is now my selected channel and component. You see, I only selected this KNDS station on the vertical component. Okay, so now I can take this trace and try to detect this earthquake, automatically. I know it's here, but I have to tell my computer this thing exists here. So I call this recursive STA-LTA function. I imported this here. You see in this line, this is imported. So I can now run it. I can show you, of course. Let's go to this manual. So the function recursive STA-LTA, what it takes, which are the arguments that you need to pass inside. A is the NumPy array, so our seismic trace data, the actual recording, and then this N star and LTA, these are the length of short time average window in samples, and length of long time average window in samples. So as I told you yesterday, this really depends on what kind of earthquakes you are looking at. If you are looking at local earthquakes, you should take short STA and of course short LTA, but this LTA should still be a few times longer than the STA. But if you look at the teleseismic events, this windows needs to be, of course, much longer because the waves are passing over your station for a longer time. So we will take this is our trace data. This is the short time window. We will take the sampling rate times 0.5. So the sampling rate here is 200 Hertz times 0.5, 100 Hertz. So we will take 100 samples, which is equal to half second. And here we will take 10 seconds for the long time window. So let's I run this now. Okay, it works. It did not complain. And now with another function that we imported before from OpsFi, this plot trigger, I can put inside the trace. So this TR that we created before, the detector that we run now, the threshold on and the threshold off. If you remember yesterday, those red and blue lines. So let's see what happens. This is our earthquake, so this one, and this is how it was detected as an event, a transient signal on the continuous waveform. So you can see the red line is the trigger on, the blue line is trigger off. So if you look at this detector, so this is what we compute with the recursive STA-LTA. You see that it jumps up very fast because the phase arrival is very strong, and then it decays. It jumps up again because of the arriving S wave, and then it decays slowly back down until the trigger off at 0.5 is set, and now there is no more earthquake. Okay, so this is useful, let's say, for some, if you want to set an alarm, like an early warning or something, because this is done, as you saw, very, very fast, and it can work easily with real-time data. The problem with this kind of detectors is if you have, let's say, swarm, so many earthquakes happening in a very short time, or a strong aftershock sequence, you will miss a lot of events because the calculated long time average will also include earthquakes themselves, so the ratio will be very low. Here we only have one earthquake, no problem, but if we would have just after it another one, this ratio for the first one would be most likely okay, but for the second one, no, we will probably miss it. So to get over this, of course, we need to use some more sophisticated methods. Okay, so now let's download some data and do some more precise things. Let's see. I will download 1 day of data from the one Slovenian station. This is for the, this is 20 March this year. And let's see what we can see on this station when it's downloaded. Okay, let's make a plot. We see something here, and we see something here, and then so this is 24 hours data. So let's make another filter. With the bandpass filter, so just we are just interested in frequencies between 2 and 20 hertz, and now we see that we have more small events. This is, I wanted to show you here this thing. So if we okay, I need to download it. Okay, so if we just plot the raw signal, we see this long. This is what? This is 3 hours. This is 1 hour and something long signal. This is actually a magnitude 7 point something teleseismic earthquake very far away. And this here is also a long signal because this is 24 hours. So this is most likely another teleseismic earthquake, or at least original one. I think that this is the day when 2 very big earthquakes happened north of New Zealand, a magnitude 7 point something and magnitude 8. So you see, we only see these 2. But if we filter down to the frequency, which is, for the local earthquakes, and make this plot, we don't see those teleseismic anymore, but we see these small, short local earthquakes. So we are interested in this, not in the teleseismic one. So as before, I will just take the vertical component, which I actually just downloaded, and make a trace, and run the detector compute. So let's see. It's done very fast because it's just 1 day of data. And now let's find the trigger of this. Yeah, you see the plotting takes longer than actual calculation. Okay, let's see what happens. I hope my computer does not crash. Okay, now you see with the threshold of 7, this is some value that you set with testing. We detected how many? 1, 2, I don't know, let's say 4, 5, 6, 7, 8, 9, 10, 11, 12, 15 events. We do not know if these are really earthquakes or just a transient signal. So this is in 1 day. Now here, this is this part here, it's a bit complex, but okay, so we will take this threshold 7 that we also put here. Off time, we slightly increase it. Then we take another function already defined from SciPy package that you have installed. It's called find peaks. So what it does, you put this detector inside, you tell the threshold that you're interested in, put a distance, something you can read more about this in this manual for find peaks. And this will actually give us it will just extract this waveform around these peaks for us so we can see what we have. So let's do this and see what it does. Okay, so you see here it's wrote down. It's with this setting 7 and 2, it found 15 events in our data set. So now I can extract these events with this function and make plots for them. So in this extract detection function, I put a trace, this one, detection times, so those peak times that were calculated here. Pre-detection, so this is 10 seconds before and 100 seconds after, so this is samples, well, this is seconds, and we will plot this. Now we can make this shorter. And let's make plots of these things. Okay, so we should have 15 pictures. Now we can go through these 15 pictures and decide what's an earthquake and what is not. So, what do you think? Is this an earthquake? Is anyone brave enough? Let me rerun this. So, okay, let's go one by one. So, let me see. Simone, the first one, is this an earthquake or not?
I think it could be, yeah.
So we can see, okay, let me make a slightly bigger plot here. So for this one, the first one, you can see that this is noise, okay? And then something happens here. The noise is not so much noise anymore. And then we have this big amplitude here and decay. So most likely this is, yes, a very small earthquake. The P arrival is here and the S arrival would be here. So next one, who's next?
I'm next.
Okay, try. What is this?
Yeah. So we have noise and from the start, and at where your mouse the pointer is, we have some event over there that we can subject it to the earthquake because of the magnitude, the peak, because of the magnitude. So at where your pointer is, I will say we have like two earthquake events over there. I'm seeing 2.
Okay, interesting. I have no idea what this is. This could be, you know, I don't know. I mean, it could be. I don't think this is an earthquake because this is very, very short in time. And you see, this earthquake, this is a local earthquake. So it takes, I don't know, let's say almost 10 seconds. This is just few seconds and I really have no idea what this is, but maybe it's just, you know, a track or
okay,
or something.
Maybe that one too is a noise, but a different noise that was recorded or what?
This one?
No,
here.
The one, yes.
Yeah. I mean, I don't know. You know, I mean, these stations are very sensitive, so maybe, you know, they were working close by, and I don't know, or a tree fell, or who knows.
Okay.
But I don't know.
From the differentiating the earthquake with the noise, I think it was, you were saying the peak, the magnitude of the peak to and
So the magnitude, I mean, this is for sure, it's some transient event, something, you know. And yes, this is, so the noise here and the noise here, you can see it's, this amplitude here is not so much bigger than the noise. Because let's say, if we look here, you see the amplitude of the noise before the earthquake is much smaller. So, you know, they are very close in scale. So, okay, next one. What is this? Who is next?
then let's be Tarek.
Tarek, guess.
Okay, so it seems that it's I don't.
You can say whatever. There is no wrong answers. So what I see here is, you know, this is noise, and then there are some longer period waves. I mean, it's not a local earthquake for sure, because this is very long for local earthquake, but maybe let's see. No, this is, let's re-download our data, the original one. Just a second, let's see if I get some idea. So 6, 9, that's 9. Yes, you see, this could be this teleseismic earthquake at the beginning. So the arrival of the first phases, because the timing is very, very similar. So maybe this is it.
Okay,
If we would use different filtering, let's say a low pass filter, probably we would see. This does not mean that this is, you know, this maybe is just local shaking, local side effect from the passing of the teleseismic wave, because the teleseismic wave has lower period noise, waves. So it's not a local earthquake, but I think it's a teleseismic one. So I think also this has, this is just a few minutes later, this is just another teleseismic phase arriving. Okay, and now this one. So who's next? Tung.
Pro.
Yeah.
Pro. Yeah, hello?
Yes, hello.
Yes, it's Yakubu.
Uh-huh.
Yeah, I have a question.
Yes, sure.
So regarding to what we these waves, the recorded waves, like how before you say something about it, like you did something which gave you much knowledge to confirm that okay, this one is this. Like, what did you do? Like,
yes, this is actually a good question. What did I do? I saw too many earthquakes. You know, for 3 years during my PhD, I was picking phases of small, medium earthquakes. So this is
okay.
just when you see so many phases, you start to recognize what you see. Otherwise, I mean, let's say, check the wait. I can try to, just a second, annotate. I can try to draw if I'm able to. So let's say a local earthquake. This is now everything in absolute should have a shape like this, okay? Because we have P and S arrival. Then let's say if you have a active quarry, so you are making explosions and you are mining for the rock, this should look more like this. So you do not have this separation of the phases. Then, I don't know, the teleseismic events will have multiple phases and are very long in time, of course. What else? Then let's say regional large earthquakes will have the P arrival, then S arrival, and then most likely surface waves. You know, you start to identify these phases.
Okay.
So it's mostly because I saw so many.
Okay. So it's like if you work with it more, you get to know them.
Yeah, I guess.
Yeah.
Okay, so Zung, what do you see here?
Yes, I think it's the small earthquake.
Yes, exactly. It's very clear signal.
Yes,
So
it was the same.
okay, now what do you think about this one? Zung, this was too easy for you. Try to say what you see here.
I think it was a small earthquake, but before earthquake happened, we can receive a lot of signal.
Yes. So, okay. Now what I think here. So this is a bigger magnitude earthquake. You see the noise is, the level of noise is very small, right? And then you have P and S arrival and some coda wave after the earthquake. While here, the noise and this signal are almost identical. So this is something, the magnitude of this is really, really small. But I think that in this case, you are right. I think this is a very, very small aftershock of this one. Why do I think this? Because the shape, I mean, I think this here is the same S arrival as this one here, but a smaller magnitude. And you have P window here, and you see something here. So maybe this is some very, very small aftershock. So yes, I think.
It's a figure is the with the S square.
Mm-hmm.
S square, not P square.
Yeah, this is S.
Yes. And after S square we can receive make some S square. Is that right?
After here.
Yes.
So this is mixture of noise and the coda wave. So the coda is this
cool.
This part of the earthquake is called coda.
Yes, coda.
And so this is a mixture of everything. So that's why it's so we don't see anything.
Yes.
Okay, now Innocent, what do you see here? Do you hear me?
Yeah, I can hear you.
Okay, I was having a question, but
yeah, okay, after.
Okay.
So do you have any idea what this is?
I don't have an idea.
So yeah, I don't have a straight answer, but this could be, again, some aftershock of this one, because this shape here, you see, it's quite similar to this one. But before when I was annotating, I said that for the explosions in quarries, we get something like this, right? So maybe this is actually explosion in a quarry. Why I think this? Not just because of the shape, but because of the timing. So you see, sometimes when you are looking at active mining, the explosions will be always at around 1, 3, 12, always at this kind of hours. So maybe could be an explosion or could be an aftershock. I don't know, but it's a signal. So for this one, I would say it's an explosion. Okay, so I think 1, 2, 3, 4, 5. Yes.
Yes.
Yes. Question, please.
You were saying about code earthquake or something. So,
Coda.
Coda earthquake. So when the event happens, what's happened after is what you were referring to as coda.
So okay, coda wave. So we have our, let's say, our P. The P wave comes, and let me try to annotate again. So the P wave comes, let's say this is our P, and then it would be like this, and then S, and it should be like this, okay? But because we are dealing with the real Earth, we get, of course, after P, we get something like this, and after S, we get something like this. And after each phase that arrive, we will get this decay. And this decay, can I choose a different color? This decay is called coda, and coda is after every arriving signal. This is, you know, it's like when you start to shake a seismic station, which is, let's say, on soft sediments, these sediments will still shake a bit after the passage of the wave. So these are kind of trapped signal, or resonance or something like this.
Okay.
Yes,
okay.
and this takes some time to die off before it returns to the previous level of the noise. So if you look at, let's say, extremely large earthquakes, this ringing, some people call it ringing, this can take, this will take days. Let's say each time that the surface wave pass your station, after, I don't know, a few hours after the earthquake, few days after the earthquake, because it's, it's going around and around and around, each time you will get a smaller ringing and smaller ringing.
Okay, I see.
So yes, this coda is a window after the arrival of the phase. I think that with Daniel you will talk something more about this coda wave, because in the noise tomography, this is what you actually look at, not at actual signal. So I think Daniel will have more to say on this.
Okay, thank you.
Okay, any other question? Okay then. So yes, we saw some impulsive signals. So impulsive signal is this, when there is a real clear change, and then the non-impulsive are this kind of signal where the change is not nice and you cannot really say what this is. So now what we will do, I will try to show you how we can, let's say, if we take one earthquake, this one, how we can automatically pick the phases. Before, here in this example, we just detected a change, so a transient change. We did not actually pick a phase, but with some changes in the code, you can actually do this. So I will take this downloaded data. Where is it? So this one, I will take it. Let me, oh no, I will maybe some other one and down. Yes, I need to download again because it's some other event. And then let me make a picture of this and let's see what we have.
Professor,
Mhm.
when do you okay, so, with filter here use you band pass, but below use you high pass. When I use you band pass and high pass.
So normally I will use band pass because for earthquakes, let's say local earthquakes, I'm only interested in selected frequency between somewhere, let's say 1 or 2 hertz and up to 20, 30 hertz, not more. So if I do band pass, it will give me real information, more information about the local earthquake I'm interested in. If I do the high pass filter, everything, let's say high pass filter at 2 hertz, this will leave everything above 2. So even information at 50, 60 hertz that do not carry any meaning for earthquake. So you will not see earthquake as nice with high pass filter than with band pass. So in general, I think the best thing to do is to always use the band pass, even for, let's say, teleseismic, but you select appropriate frequency inside. But then again, I mean, probably it depends on the application you want to do, but more or less the band pass should be used always.
If I want to consider Kozagwe, I will use band pass.
Mm-hmm.
Thank you.
Yes, yes. But you have to know, let's say, at very close distances, you will use a band pass between 2 and 20 hertz. At bigger distances, you should use band pass of lower, let's say between 1 and 10. Because further away from the earthquake you are, less high frequency content will be, because of the attenuation, less high frequency content will be in your earthquake.
Yes, thank you.
No problem. So this is still downloading. Yes. So in meantime, any other questions? So let's wait a bit more, otherwise I will restart this maybe. Okay, it's done. Now the okay, perfect. So now you can see here 1, 2, 3, 4 different stations, each station with 3 different channels. And so this is data for how long? This is 1 day. Yes, this is 1 day of the data. And you can see, let's say this station has a lot going on, while also this YAV station have some more, but KNDS and SKDS are much more quiet. For this one, say, I can tell you why it's so noisy, because it's close to a small settlement, small city, and there's a road, and that's why there is so much noise you can see here. But for all of them, you can see there is a earthquake almost at the midday, which is visible everywhere. And also, let's say this line here on this station and this station correspond. So most likely this is also something that happened and got detected by all the stations. So, okay. Now let's try to run this. This is now a different kind of trigger. And let's run this on our data. So first I filter the data, then I select only vertical, so it's faster. And then I use this rec star LTA detector. You can find more about this on OpSpy website. I use the threshold 6 for on, threshold of 1. And these are some other settings that you need to set up. So as I said, I found 6 things. Now let's see, let's plot this. I will just plot one station. Okay, as you see, there is only one earthquake. This is also earthquake, but the teleseismic one, the same thing that we saw before. So nothing too interesting. So we will only focus around this one, which is the one that you see here in the center. Yes, at 11:26. So, okay, now let's do this. Oh no, we will do this on some other event. So, okay. Now, yes, of course, I want to tell you this. So, in this example, we will use the automatic phase picking, okay? But it's very simple to do it also by hand. Of course, there is many professional software packages where you can pick the phases by hand. Simone should know, he can use Antelope. Antelope is a really big system which is run at some institutions everywhere around the world. It looks not so nice, but it's quite powerful. But if you do not work in a institution that will issue warnings, you will most likely not see it in action. Other institutions will use Seiscom free, which is another system like Antelope. Some people prefer one, some people prefer the other. But what you can try on your computers is this Pyrocco. This is it's a Python package written by some German, by the GFZ, I think, and it is able to do many things. Let's say you have here examples and notebooks. Here is how to download it and install it. And let's look at examples. So you can work with your data. You can make a database of your data. It works together with OpSpy. It has a support to read and write station XML and QuakeML files. It also has some GPS analysis modules. You can download the data with it. You can look the earthquake catalog. You can look at the moment tensors. You can make some nice plots with it. What else? This Snuffler, I will show you Snuffler later. You can calculate the travel times. This is, I mean, you can do this also with OpSpy, but this one is slightly more powerful because you can also then with these travel times, you can model the earthquakes. So you can generate a green function database and make some synthetic seismographs. What else? You can invert large earthquakes for their moment tensor and focal solution. You can work with INSAR also here. many things, but read it and see. But now, okay, now first let me show you quickly how this automatic phase picking works. So let me go to this folder. Okay, just a second. Open. So I have the Snuffler installed. Let me run it. So I will show you just the vertical seismic stations because it will not take so much time to do anything with it. Okay. Share screen. Okay, you see, this is now Snuffler. Within the Snuffler, you can pick your own phases of the earthquake. So now you can see, okay, this is say station vertical, GBAS, YAVS, and so on. So I have these stations loaded inside, and I can zoom on this data. Now you see the raw waveform, and you can easily move around. This is one earthquake, I think. Another one bigger. So it's very easy to work with. Now let's go to that. Where is this earthquake? Okay. Here you can filter the phases between 2 and, traces between 2 and 20 Hertz. Okay, so you see now clearly our earthquake. And what it means to actually pick the phases. Let me just zoom on one trace so it's more clear. Let's look at this one, which is very nice. So you see now, this is our P arrival here, this is noise. And then suddenly we have a very nice P arrival going up. So we can pick a phase here and say, okay, this is, just a second. I don't know what I just did. Can you still see my screen?
Yes, you can see your screen.
Just a second. Okay, now it's better. I need to figure out, I forgot which keys I have to press. No. Shit, I forgot. Anyway, so let me delete this one. In the manual, you you have to read, but anyway, here you can say, okay, this is my P phase, and our S phase is, so this is the coda of the P. You see how nicely it's decaying, and then when there is a big change, you can say, okay, this is now my S arrival here. What you have to have in mind is that P arrivals are normally, if everything is okay, are always picked on the vertical channel. While if we are looking at S arrivals, you should pick it on horizontal, not on vertical, because maybe S actually happens here because where you already have some different change you see here, but the vertical channel is not so sensitive. Let me reopen this with only one station. Okay, let's find this earthquake again. Yes, okay, so you should pick P here on the vertical and S on one of the horizontal. So S should be, I would put it here. So this is phase picking. It's very easy. You can also install this software on your computer and try to play with some data sets. Okay, what you can also, let's say, quickly make some amplitude spectrum. No?
Prof,
Yes.
please, before, how did you, this interface that you are showing us, how to pick the first arrivals, how did you come here? Like, how did you come here? The navigation to this part.
To what?
The navigation to this part, this, I don't know what you opened and you came to this interface.
I don't know if I understand you. So you install the software, you load your data in.
Okay, it's a different package that we have to install.
Yeah, this is, it's here, wait.
Okay.
It's called Pyroco. I put a link in the Jupyter notebook, you will see. You have a link to it, and I mean, I just wanted to show you here that, you know, this can be done very simple. The only problem is that phase picking by hand takes a very long time, because you have many stations, many events, and it takes a lot of your time. Yeah, okay, so anyway, let's go back to the Jupyter notebook. So here, Pyroco, you see? Here I put a link to this this software that you can install and try to play with some data. Okay, and then let's say this PhaseNet, the link here, this is it's a link to the paper about how to perform phase picking with the machine learning. So you can read about this to get some idea how this is done and how it works. Okay, so now let me run this. Okay, and download the catalog. So now let's try to you know, pick phases on some earthquake with automatic methods. So I'm interested in this time period. This is the same as in the first notebook that I showed you. So, and this latitude and longitude, and first I download the catalog.
So I have a question.
Yes.
How can I define the area of interest?
So here, in this example, we set a minimum latitude and maximum latitude, 45.53 and 45.78. And the minimum longitude and maximum longitude.
I mean, why you already choose this some numbers here? How can I?
Why I chose this?
Yes.
Because I know that there are earthquakes here. I know the earthquakes are here and the data is available. So you know, if you want to do this for Vietnam, I don't know what you will get.
Vietnam is, I think, it's so small earthquake in south.
Yeah. South has earthquakes, yes. But
not.
No, the problem, let's say, for Vietnam is I don't know if they, you know, how they share the data. Is it available here, let's say, on the ISC catalog or not? So let's say if you want to test this, how it works, maybe, you know, select area in some very active place. I don't know, try with Central Italy or something like this. Because then if you want to download the station waveforms, again, I mean, I don't know if Vietnam is sharing the data or not. So maybe, you know, try to download the data from Central Italy. It should work.
Yes, thank you.
Yes, and of course you can try with Vietnam or with Ghana. Everyone can do what they want, and no, it's good because you will see. I mean,
Yes.
you will see if the data is there or not.
Okay.
Yes, but if you use let's say if you use this ISC for the catalog, and if you do not get anything, try also using different, I don't know, iris. Maybe you will get some events like this. So check, and try to play a bit and you will see. Okay, so we got 595 earthquakes, but because we just are interested in one specific one that I know of, I will filter this catalog between these two times. Okay, and this is now I only have one event in my catalog. The magnitude of this earthquake is 1.4. So now let's set the origin time that we can use later, event latitude, event longitude, and depth of the event. Okay, and now let's select this data for phase peaking. So this is my data now. I will filter it between 1 and 30 hertz, and I will cut around this earthquake that we selected here, 5 seconds before and 1 minute after. Sort this is, it's not, we can do this. And I will make a plot of this so we see what we are working with. Okay, this is our earthquake. So now let's run this picker on it. So we will use the so-called AR picker. If you go to the manual of OpSpy and search for this AR picker, you will get all the information that about these values here, that you see some strange numbers. So what we have to do now to run this picker, this here I create two empty dictionaries. So dictionary is, like a dictionary. What you will get inside here is some name of the name station. It will be a name of the station where this phase was picked and a value of time when the peak happened. And because we will look through available station, this dictionary will fill with all these stations, so station and the peak time. And the same is for the S phase. We will get a station time, name and station time for each of the phases. Then what I need to do for the AR picker, I need to specify vertical channel, north channel, and east channel data. So I do this by selecting these different components and setting them to these names. And then I loop through these three traces, and on each trace I run the picker. You will see it sounds complicated, but at least we get some result. Okay, so I run this. It's very fast because we don't have much data. Here I print. Okay, you see that this is now our full dictionary. Before it was empty, now it filled up with these values. So this is, say, station, and the peaked time is 8.86 seconds. This does not tell us much, but you will see we can get, out of this, we can get a real timing. How? We know that, this time window when we start, so where is this written, just a second. So we start our time window at origin time of the event minus 5 seconds. So we know when this starts. So we can just take this origin time minus 5 seconds plus this, and we get a real value for the timing of the phase. So now I can plot this picked phases on our data. Let's see how this looks like. And this is it, you see, we picked automatically phases on all these stations and channels. So P is vertical, I mean, it's P arrival, the red one is P arrival, here, 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 and blue one is S. And what you can see is that I did not really set this very nice. So these values here. You can later, if you want, if you read in the manual about this AR picker, you will understand exactly what these numbers here are, and you can change them a bit and try to get a better figure here. So what's wrong? P arrivals are very nice. You can see when the phase comes. If we zoom a bit on this, you will see this better, but it's quite okay. Then if you look at the S phase, okay, here for this Canada station, it's quite good. And also here for the SKDS phase, but here, let's say for voice, you see it's here, but the change is already, let me zoom in a bit. The change is here, but the S arrival peak is here. So this is not tuned very well. So what does this mean? Now if we put these P and S phases in our software to calculate location, the location will be slightly wrong because we will use wrong S arrivals. Then what we can do, we can also, calculate the theoretical phase travel times to see how well our picked ones work. So you can. Yes.
I have a question. So with this, the phase pick out, right? It's about the phase picking, the arrivals. So with what we initially did and this automatic phase picking, which one is more accurate? Like,
so if you have time and if you really want to do this, you should do it by hand, because by hand you can really, minimize the error, because these automatic functions are always prone to some errors. These errors will not be big, but to get, if you have a very nice network and you really want to get a good location, you should do this by hand. But as I mentioned before, these machine learning algorithms are becoming more and more powerful. And I tested some sequence with machine learning, and I checked how well these phase arrivals are, and they are very, very good. I mean, they are becoming comparable to what you can pick by hand.
okay.
So if you have a possibility, let's say I can show you, what is it? Let me put this link here. So you will also have more information here. I will send this to you later. Okay, you have two links now here. So the machine learning performs very well. It will pick P and S phases even for very, very small earthquakes very precisely. And this is good, not only because it works faster than we do, but it's also good because the errors will be consistent. Let's say on a good day, you pick P and S waves in one way, but then, I don't know, you have a headache and you don't work as you should and you do not pick the phases correctly. Or maybe someone else does it instead of you. So one day one person is picking the phases, the other day another person, and these are now not consistent anymore. But with the machine learning, this will be always quite the same. So this is one example. This works you know, if you follow the tutorial here and installation, you can run it on your computer and try it. It's very simple to set up. And this is the one that I tried. So I put link here in the Jupyter notebook.
Thank you.
Yes, no problem. Okay, so the theoretical phase travel times. So to calculate the theoretical P and S phase, let's say, you can calculate also others. You need velocity structure, you need the location of the earthquake, and you need depth of the event and the location of the stations. So we will use already built-in velocity model to OBSPI. It's called ESP-91, but you can check in the manual, there are many more available, or you can also generate your own. It's a bit more complex, but not so hard. So let's do it. We set this model up. And now with this function, get ray paths, here we say, okay, this is, I want the first P and the first S. We say, okay, the depth of our earthquake is 15 kilometers. We could use exactly this one here. Just a second, where did we save it? So event Z. Let's use it like this. Distance in degree, we could calculate the exact value, but this would complicate our code a bit. So I will just use 0.5. And I will generate a plot what these theoretical waves are. So you see, this is our earthquake. This is our station 0.5 degree away. And this is the direct P, this one here, and direct S. It goes down and then back up to the station. Sorry, this one is not direct. So this is just to visualize what this is. So now what we can do, we can actually take each and every station in our inventory that we have to read here. I will create two dictionaries like before. One is for P and one is for S arrivals. And now I will calculate P and S arrival for each station in the Slovenian network for this earthquake. So what I do, I look through the stations. I calculate the distance in degree. So this is done here. And then I take the depth of the event and the distance between the station and our event in degrees. So before I set it here to 0.5, but here I will actually use the actual value. And then I will save this into our dictionary here. Okay, it takes some time. Okay, now I can print, let's say, let's look at just the P phases. Now you see we have for all the stations theoretical times. And let's compare these theoretical times with those that we made before with automatic picking. Just for, of course, for a few stations, because we do not have all this information. So, okay, now you see red color is automatic detection. Green color is calculated P arrival. Blue one, dark blue is calculated S, and light blue is light blue is calculated S, and dark blue is theoretical, sorry, the one that was picked. So you see, in some ways, I mean, it's not so different than what we did with our algorithm. In some phase examples, it works better. In some examples, it works worse. But you know, you can see that it's very close by. What you could do is use some other velocity model, and you could get much better results. Now, why these differences? The difference can be, of course, because of the velocity model, or because the location of the earthquake that we put in this calculation here is not exactly correct. Maybe we mislocated it. Okay, so now I can take these automatic phase arrivals, and I can locate this earthquake. I can try to compute its location. For this, we will use the so-called non-lim-lock software. Here is the link to it. You can read about it here. There are many papers that use it. You will not be able to do this except if you set it up on your computer and do some pre-calculation. It's a bit complicated because first you need to calculate the travel time grid, the velocity model, and observed travel times. So this is, the software is very nice for calculation location, but if someone does not show you how to do this, it can be a bit complicated. So maybe, let's say, on Friday, if we have more time, we can also look how to do this on your computer. So, okay, let me take our automatically detected P and S phases and save them into the file which can be read by the software. So this is done with this code. I will not explain to you, it's too complicated what everything is, but so now I generated this file. I can show you how this file looks like. Which one is it? LLL. So this one. So you see now for each station and this is vertical components of my station. I put observed time, so the one that was calculated with automatic detector. And I can run this non-lim-lock now on my computer with some parameters, blah, blah, blah. Now it's running.
What's a simple question?
Mm-hmm.
What's a simple question in the file?
Sorry, what?
I mean, what's a simple question?
Where is it?
Is inside first four, you have phase file dot right below.
Phase file?
Below.
Below? Where?
Phase file dot right.
Phase file. Okay, here.
Yes, inside you have question.
These question marks. This?
Yes.
Okay. What is this?
Yes.
So this function here, this will write to a file, and this is our file. Okay. Yes. So these are these question marks here. This is the input to the non-lim-lock. This file is an input there, and you can specify here some value, let's say a location, channel location. This is sometimes it's 0, sometimes it's 1, or if you don't know it, you can just put a question mark. So that's why I put questions mark here. This is, I mean, the important thing for this file that we put to non-lim-lock are these timings here. I will check for the link for this phase file that we use with the non-lim-lock, and inside it's explained what you can put here, but don't worry.
Thank you.
Yeah, okay. So now our earthquake was located. Okay, it says one earthquake located. Now let's see. So in the catalog that we downloaded before, the location is given like this. So latitude 45 something, longitude 14 dot something, and the depth 12.9 kilometers. And our new location, using a different algorithm, we get similar latitude, similar longitude, but slightly deeper event. This is most likely because we used different velocity model. So we can also check on the map where this is. Just a second, let me open the map. So let's start Google Earth. So the location given by the catalog that we downloaded before . location of that earthquake is this one. So it's here, the red star. Just a second, let me make this a bit clearer. Oops. So it was it's here, okay? And our location, the one we got, should be quite close by. Okay, it's here. So the difference is few what? It's 3 kilometers distance between there and our earthquake, which is reasonable. Different methodology, different locations, of course. Okay. Let's go back. You see my notebook?
Yes.
Yes,
Okay.
yes.
So the last thing for today, we can calculate now the local magnitude of this earthquake. So we will only select the stations on the east direction to make everything simpler. So let's do this. So these are 1, 2, 3, 4, 5, 6 stations. In these 6 stations, I will try to calculate the magnitude. So what I first have to do is to remove the response and convert our data to the displacement, so to meters. Okay, because in the formula here, we use the amplitude in micrometers. So I need to, I showed you the function before. Okay, so I convert this to the displacement. Now you see it's slightly different than before. Okay, and now I will call this for each of the traces here. I will call this position finder. So the position finder will find the maximum amplitude and give it will return the value where it is. And for each of this one, we will take a picture, so you will see that it works as it should. And then the next magnitude, local magnitude, we take, as I said before, we will, for each stations, we will say that it's 29 kilometers away from the earthquake, which is not actually the case. It's close by because these stations are at these distances. But we could, inside of this code here, we could calculate the real distance, but I ran out of time to actually do this, but it's very simple. You can follow this example here with the theoretical travel times, and you can do this correctly. So let's run this. Okay, this is now the magnitude that was given by the catalog was 1.4, and the one that we calculated is 1.6, which is almost identical. And you can see the maximum amplitude for this station is here, where the red line is, and this is where they cross. You get this value back, and for this station here, for this station here, for this station here, and so on. So we successfully calculated the magnitude. Okay, this is it for today. If you have any questions, please ask.
I have a question with the first lecture. I have a mistake. Can I share my screen, Professor?
Yes, sure.
Yes.
Just a second. Okay.
I cannot share.
You cannot? Just wait. Can I do this?
Oh, now it's fine.
Okay.
Okay. I try again the first lecture, but see here, I have an error.
Yes, because where did you get this trace? What is this? So if you want to, let's say, if you want to do this data for the the one that you have in the window above.
Yeah, I do like you say before.
Just a second. Let me turn on the annotate. So if you want to get the data for this say, so instead of trace here, you must write say 0 dot I'm terrible data. So instead of trace, put say 0.
0.
Yeah, like this now data.
Oh, I will try.
Yes, because this trace, you did not define what this is. If you would write here trace equal to say 0, then you could say trace dot data. But now currently this trace is nothing. It's not really defined.
I don't know.
Yeah, before we had this, if you go up. Okay, maybe, yes, no, I understand. Can you go slightly down? I think this comes from the fact that the first line here in this window before was called trace equal to select station. So maybe I made a change. So this, wait. This, I think that before it was written instead of say here, it was written trace. Okay. So if you change this to trace and delete the say 0. Yeah, if you do this like this, now press enter. Oh, sorry, run it. This. Okay, and now go down, go to the next.
This?
No, this will not, it will not work. Can you run it? Yes, it will not. Now you have to say here trace for each of every. Can you, okay, you know what's the easiest way? Go up.
Up.
Okay, stop. No, after the picture. Put this here. At the end here, put square brackets and 0.
I do.
Square brackets, so the
square.
Without space. Yes, and inside put 0.
Yes.
Yes, and now delete in the next line, delete the square brackets part.
Yes.
Okay. Now run it. Okay, now go down to the next one. Yes, run, this should work now, yes. Yeah, go down. Yes. And also these others should. Okay.
Yeah.
No, because I remember I did, while we were talking, I did a change and, okay.
Thank you so much.
Yeah, no problem. So anything else?
It's very well.
Any other questions?
I have one curiosity.
Mm-hmm.
The STL-LTA method and the phase picking are working only on one trace at a time?
No, I think now, if I remember correctly, in OpSpy, if you put multiple traces inside, you can do it, but I think it will return only the detection of the event, not actual phases.
Okay.
I'm not exactly sure. You should check in the manual, but you can, if you work with only one. No, maybe that one is just for actual events, and then the actual phases are calculated in a slightly different way. No, I don't really remember.
Okay. No, it was just a general question if it's Yeah, the phase peaking is based on the single traces, on the single components.
Yeah, no. I mean, in general, this is based on single component. Yes.
Okay.
But the function that is given here in OPSPI, I don't know exactly.
Yeah. Okay.
But otherwise,
it's possible to detect the phase simultaneously on the three components?
Yeah, sure. There is, now I don't remember, I read about some function called Subspace Detector that needs free component, and it works with free component. It gives you, I think for that study, it was very good, okay. But I never really used it. But to maybe, I mean, you can, the STA LTA is normally, the classic STA LTA is one trace.
Okay.
But you have many different kinds of STA LTA. Even in the OPSPI, you will see there is not just one.
Okay, thank you.
Okay. So anything else?